Hello students, welcome back to JCE Connect series of lectures. So in this particular lecture I will be deriving the equation for length of backwater curve, that is expression for the length of backwater curve. About backwater curve we have been discussed in the previous lecture, backwater curve and the flux, where it takes place, how the backwater profile will be. These all things we have been discussed in the previous lecture. So in this particular lectures, what is the length of backwater curve? Okay, so let us start the equation for the backwater curve. Here this is the bottom of the channel, and consider this is the bottom of the channel. You know already these things. This is the direction of flow, and this is the obstruction along the direction of flow. When there is an obstruction along the direction of flow, so before reaching any obstruction, the flow depth was this one. Then as it approaches obstruction, then gradually the flow depth increases like this, then it falls. The point where it starts rising, say section 1, and point where it reaches the maximum height, that's section 2. The length between these two sections is called as length of backwater curve, and the profile of the water curve behind the obstruction, whatever you get, it is called backwater curve. The rise of water behind the obstruction or the upstream side, that is called afflux. Okay, this is called afflux. The rise of that is if you take this as a y2 and this as a y1, y2 minus y1 is called as afflux, and the length between section 1 and 2 is called as a length of backwater curve. So now we are deriving the equation for this L now. Okay, so let us consider, this is the channel section I have considered. This is the datum line, marked here datum line, and this is the channel bottom. Then from the datum to the datum line to the bottom of the channel I have taken as a Z1. Then from the bottom of the channel till the free water surface is a Y1. Then the velocity head I have considered at section 1. Similarly at section 2. Then here the datum is merged with the bottom of the channel. Then it is starting from y2 plus velocity head plus energy loss here, and this pink line, dotted line, indicates energy gradient line, that is energy at section 1 and this is energy at section 2, and energies go on decreasing along the direction of flow because of the friction, and the slope of energy line is represented by SE. Then the slope of the bed of the channel is represented by SB, and the length between the section 1 and 2 is represented by L. I hope it is clear, this figure. And this figure, that is a flow through a rectangular channel, and here the depth of flow is varying. Okay, then here it is given, consider the flow of water through a channel in which the depth of water is rising as shown in the figure. The depth of water is rising, so this one, like this, it is rising. It is being shown in this figure here. The depth of water is rising. At section 1 the depth of water is y1, and section 2 depth of water is y2. Let the two sections, that is section 1 and 2 are at such a distance that the distance between them represents the length of backwater curve. So here I taken section 1 and section 2, the point where the water starts rising and the point where the water reaches the maximum height. Between those sections, whatever the length you measure, that is called length of backwater curve. For this we are deriving the expression. So let us take y1 as the depth of flow at section 1 and y2 as the depth of flow at section 2, and v1 is the corresponding velocity at section 1, that is velocity of flow at section 1, and v2 will be the velocity of flow at section 2. Then the SB represents the bed slope. SE represents the energy line slope and the length represents the length of backwater curve. So these are marked in a figure. So Y1 is here, Y2 is here, SB is here, SE is here. SE represents the slope of the energy gradient line, SB is the slope of the channel bed, then Z1 is represented, Y1, everything is been represented in this figure. Okay, next, so applying Bernoulli's equation at section 1, 1 and 2, we know the Bernoulli's equation, that the equation represents the energy of the flowing fluid. If you apply at section 1, 1, we get the energy at section 1 as Z1 plus Y1 plus V1 square by 2G. Then at section 2, Z2 plus Y2 plus V2 square by 2G plus HL, that energy loss. So if you write energy at section 1, here energy at section 1, and this is energy at section 2, energy 1 and energy 2. Here energy is Z1 plus Y1 plus V1 square by 2G. Here Z2 plus Y2 plus V2 square by 2G plus the loss of energy. Okay, then this equation equals, let us call this equation number 1, where HL represents the loss of energy due to friction. This HL can be written as HL equal to SE into L. Then that is, so if you look at this figure, this one is the slope of energy line. We can take the tan of SE is equal to what? We can write opposite by adjacent. Opposite is what? HL divided by L. This is the opposite and adjacent is L. Okay, for a small angle of theta, or you can say the small angle of slope, the slope is very very small, so we can take this directly, SE equal to HL by L. Then HL will be what? SE into L. The same I have taken here. Okay, so that is tan of SE I have taken. For a small angle, the slope is very small, then the tan of SE will almost equal to SE. Therefore, SE will be HL by L. From this we get HL equal to SE into L. I hope you understood this one. So this I have written here. Okay. Also taking datum line passing through the bed of the channel at section 2. So that is Z2 equal to 0. At section 2, this datum line is passing here. It is almost nil here, 0. So there is no datum here. So Z2 will be 0 here. Here Z2 will be 0. Okay. Then when Z2 is 0, the equation 1 becomes Z1 plus Y1 plus V1 square by 2G is equal to Y2 plus V2 square by 2. Z2 will be 0, V2 square by 2G, then this one, HL. Then also from the above figure, we can write Z1 equal to SB into L. So it means, so in this figure, you can see here, Z1 can be written. So again, this is the slope of the bed, making an angle of SB. Again, you can take the tan theta here, tan theta or tan of SB. So tan SB will be opposite by adjacent, Z1 by L. And for a small angle, this is very small, it is taken as a mild slope, almost nil, very small. And for a small angle of bed slope, then that can be taken as SB into L, like this, SB into L. Then substitute here SB into L plus Y1 plus V1 square by 2G. We have substituted this one and also this one. Y1 plus V1 square by 2G. Then Y2 plus V2 square by 2G plus SE into L. Then take this term on the left hand side, SB into L minus SE into L. We get this term. Then Y2 plus V2 square by 2G, one term, minus Y1 plus V1 square by 2G. Then take L out, we get L SB minus SE. Then this is what it represents, energy at section 2. This means energy at section 2, that is E2. And this represents energy at section 1, that is E1. Then the L can be written, E2 minus E1 can be written, then L will equal to this one, E2 minus E1 divided by SB minus SE. Okay, this is the expression for length of backwater curve. If you want to calculate the length, how much length the backwater is having, you can calculate energy at 2 and energy at 1. The difference of that energy is divided by this SB minus SE gives you the length of backwater curve. And next, so the values of slope of energy line means SE, that is a slope of energy line, is calculated either by using the Manning's formula or by Chadji's formula. It is given. Okay, you have to use either by Manning's formula or Chadji's formula. Then the mean velocities of, that is the values of velocity, there is a mean values of velocity, depth of flow, hydraulic mean radius, etc. are used between sections 1.1 and 2.2 for calculating the values of SE. Okay, so you have to use the mean values of velocity, depth of flow, hydraulic mean depth are used between section 1.1 and 2.2 for calculating the slope of energy line. To calculate the slope of energy line, you have to use either Manning's formula or Chadji's formula. Okay, so this is the expression for length of backwater curve, and this is also very important. Many times the problems will be asking on these questions. You have to remember this formula is 2 minus E1 divided by SB minus SE. I hope you understood this one. This is very simple. So this is the length of backwater curve expression. So expression for the length of backwater curve. Okay, I hope you understood this one. Please practice this derivation and also remember the equation for length of backwater curve. In previous lecture we have calculated the differential, that is a differential equation for gradually varied flow, that is dy by dx, and this is the length of backwater curve. Thank you.